Utility of logarithm. This is something that I want you to read also, pausing the video right here. It turns out that in the early days, when there were no computers, no calculators, we carried a little booklet called the table of logarithm, and so we were able to find the logarithm of any number in there, base 10. And if we needed to do a multiplication, we'll add logarithm, and then we find what was called the anti-logarithm, which is simply 10 raised to that power. And if you want to find a table of logarithm, you can go to this website. I'm going to pause. And in this website, we find definition of logarithms, and then we have a table of logarithms right there. And so if you were looking for something like 2.13, you will go 21, 3, and there's something called a mantissa, and you will dig that out and use it in multiplications and so on. So going back to our document, we have, for example, you're a student in 1966 and you're asked to find C equal to the product of 345, 67, and 32.5. You can do it by hand, or you can do this. Okay, when I take the logarithm of Z, the logarithm of base 10, actually, I forgot to put log of base 10 here because we were using logarithm of base 10. And so I calculate those logarithms separately. This you will read in a table of logarithms, and then add the two together, and raise 10 to the sum. That will be the anti-logarithm, and this will give you your result. Now, because of round off, this should be equal to 5 right there, and you can check multiplying the two numbers, and you see that you get the same result. A practical application of logarithm was an instrument called the slide rule, and you could go to this website, and you will find a picture of a slide rule. The slide rule had a sliding rule in the middle, and you have this C and D scale that you can see right there. Were very useful because you were adding logarithm. For example, here you have the number 1, and here's the number 2. This, what you're marking right here, is 1.2. So you put the 1 in there and say if you want to multiply by 2, you get 1.2 times 2. You will read 2.4 right there. So the slide rule has a logarithmic scale, and you will add logarithm to multiply, you subtract to divide, and so on. And that was the tool that scientists and engineers carried with them from the middle 1600s until the early 1970s. That's when the electronic calculators were invented or developed. Logarithmic calculations in Maxima. Well, the function log of x is the natural log. Log 10 that I defined before is the log of base 10. Log xb is for any base b. And these rules that we presented earlier for multiplication, division, and powers will apply them like that. But nowadays, there is not a strong need for using logarithm for those calculations because we have calculators that do those things straightforward. But there are still many laws of nature that follow logarithmic rules, and so there's still a lot of application for logarithms in science. But I'm going to show you examples here for calculating calculating a product of logarithms, a product of a number by using logarithms. First, we take the values of a and b, take the logarithm, I call it LA, LB, and base 2, and then sum those logarithms and then raise 2 to the s. And if we do the product, we obtain the same result. Example 2, calculate the division. Again, you can follow this is base 10, and then we have to use 10 to the d. D is the subtraction of that. Checking with the direct solution to get the same result. And a power, a to the 1.25. The log of a is LA 0.94, raised to the 1.5 gives you this logarithm, and then this is a natural logarithm, so give me the result, and it would check the power here, it will get the same result. Inverse functions, if you have logarithm of base b, is b to the y, logarithm of 10 is 10 to the y, logarithm of a is e to the x, which is called the exponential function. I'm going to draw for you here the logarithmic function. Starts from minus infinity, it grows and then it slows down. And I'm going to draw for you the exponential function. It starts from 0 down here and it grows exponentially. If you heard the term it grows exponentially, it's because it grows very fast when you get into the positive values of x. Exponential equation, for example, if you're given so like 3 to the x equals 60, you can take logarithm of both sides and then use the rule of the logarithm that you can take the exponent to multiply the logarithm and find the value of x. So for this case, we'll find x equal to 3.72. For example, 5 raised to the 2x minus 1 equal to 1.5. Take logarithms. I'm taking logarithm of base 10 right here. And you got the exponent is 2x minus 1 multiplying logarithm of 10 of base of 5. And from there you can isolate x to give you this result. Determine the number of terms in a geometric progression. This is something we haven't done before because we need logarithms to calculate. So I'm going to clear all the values here. We know that the n term is equal to a r to the n minus 1. But if I want to find n, I need to take logarithms to lower that n from the exponent. And then from that you get this formula that will give you the number of elements with this formula. For example, determine the number of terms in a geometric progression 2, 6, and so on. We take a equal 2, the ratio is 6 over 2, and the last term is 1458. So using the formula, we encounter that n is equal to 7. Finally, converting logarithm of different base. You can follow the reasoning here, but basically when you're trying to find the logarithm of a number a on base a, you can take the natural log of a divided by the natural log of a. And that's what we came up with this formula. Determine, that, for example, the logarithm of base 2 of the number 3110. Take the natural log of 3110 divided by the natural log of 2, and I give you 11.6. We can check here. Well, we can do it using our function in general and check 2 to the and number gives you 3110. Logarithm of base a of 5240. You can do this, or this use this formula or this equation or this function and calculate the value. Again, here numerical error should be 5240. You give it 5239.99995. All right, so this is the presentation about logarithms, and with that we conclude this particular video.